the phosphorus preparation of alcohol in that class. Actually, in the last class, you can see the recording. Okay. And we were just doing nucleophilic aromatic substitution reaction. Okay. So in this nucleophilic aromatic substitution reaction, yeah, okay. So in this nucleophilic substitution reaction, what we have seen was in the last class that if you have chlorobenzene and if you take NaOH, the Cl is substituted by OH group. But it is very difficult to substitute Cl by OH group. The reason is the one which we discussed, that the chlorobenzene is actually resonance stabilized. Okay. The chlorine is having the lone pair of electron. Okay. And these lone pair of electrons get into the benzene ring. So these lone pair are the pair of electrons which are not which were earlier not participating in the bonding, but because the benzene is having the lone pair, so they actually participated. So look here, one of the lone pair got into the ring, and that because the Cl is giving its pair of electron, so you need to accommodate, in order to accommodate the pair of electron, the pi electron need to be pushed aside. So that's what I did. Okay. Here, as you can see over here, so this is the resonance structure of chlorobenzene, and because of this chlorobenzene, this carbon and chlorine bond acquire double bond character. Okay, and because they acquire double bond character, it is very difficult to remove chlorine, right? Because chlorine actually is bonded through double bond, so it is difficult for us to remove. There is an overlap which happens between the chlorine and the benzene ring. Okay, this is the benzene, the electrons of the benzene. Okay, and actually there is a overlap. So suppose if you want to react it with NaOH, it is not easy. That's what we discussed in the last class. You can just go through it, and you can understand. Though I'm giving you just a brief review of what we did. Okay, so you need to, if you want to react with NaOH, you need high temperature, right? So if you want to react with NaOH, you require very high temperature because the chlorine will not come out. It is doubly bonded. It is having double bond character. So you took NaOH, but simple NaOH will not react. Okay, you took very high temperature and high pressure, 350 degrees Celsius and 300 atmosphere. And that led the OH minus to attack the chlorobenzene. Is it clear? So what happened here is, so you can see I have shown here, you require very high temperatures, okay, and very high pressure, so that the OH can have sufficient energy to come and join to the benzene. It will be repelled away by the benzene ring, right? And because it is the benzene is already having loose electrons, pi electrons, and the Cl minus, if it comes, Cl minus is also having electron, that Cl minus will be repelled away. Okay. So how you ensure that the Cl minus has sufficient energy to come and join itself to the benzene ring? Okay. You took high temperature and pressure. That's what you can see here. High temperature and pressure. Okay. Clear? So with high temperature and pressure, the OH minus displays the Cl minus. Right? If you have nitro group present, the reaction will become a bit easier because the nitro group pulls electrons, and that makes easier for the OH minus to come and join. The nitro group has a tendency, nitro has a plus charge. So that plus charge pull electron from the benzene. So here you have plus charge, and plus charge. And the OH minus will come and join here. Okay. And it becomes a bit easier. You can see the temperature which is lesser. And in the same way, if you have 2 or 3 NO2 groups, it becomes further easier for the OH minus to come and attack. Okay, is it clear? So the OH minus will come and attack here because the NO2 is bringing positive charge. This NO2 will bring positive charge at this position. And here also this NO2 will bring positive charge to these positions. So because of 2 NO2 group, the ring is very less electron rich. Okay, it is having positive charge density. And you can, but we are bothered only about the place where the Cl is attached. So NO2 OH minus can come and join in very easily. Clear? So I hope this is clear. So, but you need to take high temperature for normal substrates. Okay. So let's see the mechanism. OH minus comes and join in. The Cl minus it attacks at the position where the Cl minus is attached. The pi bond is shifted aside. It appears as negative charge. This negative charge can move in the ring. Okay. And when it arrives at the para position, it is stabilized by NO2 group. NO2 group also pulls this minus charge and make it more stable. Okay, this is how it is happening. Okay, is it clear? So, and finally what happens here is, this is an intermediate. When the OH minus attack, the ring acquire minus charge, but this minus charge actually can't continue as it is. It can't stay like this because it is an intermediate. Okay, it need to recreate the benzene ring. And how that benzene ring is created? This minus charge come again try to form the double bond, and the Cl minus will be pushed away. Okay, it will be pushed out. You can see here, and you have benzene. Okay, is it clear? Is that so? Yeah, let's do one question. So you need to compare the rate of the reactions, right? Yeah. What should be the minimum temperature? Yeah, the minimum temperature, if you have simply chlorobenzene, actually it is 350, around 350 degrees Celsius. But as you have more and more nitro groups, okay, it becomes easier and easier because the nitro group bring in the positive charge on the ring. And that actually helps the OH minus to come and join itself to the ring because OH is negative, and if you have NO2, the OH minus can come in more easily, right? Okay, so let's do some problems, and with that we can understand it in better way. Actually, this is the one which we studied is the preparation of phenol from chlorobenzene. Okay. It is also known as Dow's process. and it will be we will again going to see it in the next class, okay, in the alcohol next chapter, okay. So yeah, let's do this question. So you have to arrange the compound in the increasing order of rate of reaction towards nucleophilic substitution or nucleophilic aromatic substitution. You can think of OH minus coming and attacking at the Cl, and you need to tell me where the reaction can happen more easily. Okay? Yeah, tell me. Where it can happen more easily. So one is chlorobenzene, another is you have a nitro group at the ortho position to the chlorobenzene. Okay? And in the third C option, you have nitro group at the meta position of the chlorobenzene, right? So just tell me where the reaction is going to be very easy, where the reaction is going to be very difficult. Okay, you need to look at the electron density of the benzene ring, how it is changing with the NO2 group, and where the positive charge is coming, and is the positive charge helping the reaction to happen easily. Yeah. So I can help you out. Just I can give you a hint. Okay. This is NO2 group. I will write it in more expanded form. This is the double bond of the benzene ring. So NO2 will pull electron, and when it pulls electron, it brings in a positive charge. And the positive charge actually appear on the nitro group at the ortho and para position with respect to the nitro group. Okay. So you can see here. So you don't have to write all the structures again and again. Just what you can do here is, okay. What you can do is, yeah. First one, yeah. Okay. Yeah, good. So you wherever the NO2 group is there, just put a positive charge at the ortho and the para position with respect to NO2. So this is the opposite side. Just adjacent and the opposite side, put a positive charge. Same is the case here. Also put the positive charge at the adjoining positions and the opposite place. Okay, right? And this is how it is happening. Okay, and now what to do? Now you have to compare the rate of nucleophilic attack. So if you have positive charge, it makes the attack of nucleophile easier. Is it clear? The attack of OH minus is going to happen more easily, right? Clear? At this position, but here you have NO2 group, but the attack, this NO2 group is not properly placed. It is bringing in the positive charge, but it is the positive charge is not at the position where the Cl is connected, where we are doing the reaction. So it is not going to increase the rate of the reaction by much extent. So B is going to be the fastest one and A is going to be the slowest one because there is only chlorobenzene. There is no nitro group, and because we are attacking nucleophile, we want the OH minus to react more quickly. For that, we need positive charge. Okay. So increasing order of nucleophilic substitution reaction, the least is A. Okay, and the maximum is B. So and C will be somewhere in the middle. So third option is the right option. Okay. So I hope you understood this. Okay. Here. So this is so nucleophilic substitution reaction. Just keep one thing in mind, and that is if you have positive charge, more positive charge, the attack is going to happen more easily because the nucleophile will get attached more easily. Okay. Yeah. So let's do one process again, the same question, and yeah, tell me which of the following is going to be the right answer of this one. So which of the following is, just you need to remember the name. Okay, as this is a name reaction, right? Clear? So which of the following is going to be the method which is known as Dow's process for the preparation of phenol? Dow's process for the preparation of phenol. Yeah. Yeah, phenol actually is prepared from many methods, and let me tell you, all these reactions are preparation of phenol only. Okay, the that is phenol by different means. Okay, one is from chlorobenzene, the first one. The second one is actually from isopropyl benzene. Okay, and the third one is benzene sulfonic acid. Okay, so all are methods of phenol preparation, and which one is going to be known as Dow's process? Just now I told you. Yeah, this is very important. Just you need to know the name. That's it. So it is actually, yeah, A option. Correct. Chlorobenzene is the Dow's process. And what the name of this B? This B is also very famous and it has a very special name. Yeah. This is isopropyl benzene. So if you uh, have studied, or we will study, we are going to study it again. Okay. This is cumene hydroperoxide method for the preparation of phenol. So you prepare phenol by isopropyl benzene. Okay, this is, we will cover it in the alcohol chapter. So let's do this basic question, and this covers everything about all the substitution reaction. All types of substitution reactions are covered in this. So why we have acidic solution and what is the reason for this? What kind of mechanism is this? Yeah. So will the BR come out easily or not? In the first case, is it going to come out easily? It will come out. Yeah, why it will come out? Because yeah, yeah, that because the carbocation is very stable. Okay, you can see the carbocation is very stable, and if the Br comes out, and this is which mechanism? This is phenyl. You have CH3, CH3, and the Br can come out very easily. Okay, and this pH will undergo resonance. Okay, and the ethanol is going to attack here. So ethanol will join itself and the H plus will be removed. So it will be acidic solution because the final answer is going to be PHC. Okay, ethyl and HBr. Right. So this is which mechanism? Any idea? Yeah, the mechanism in which yeah. Just now you can send me the message, I think. And this is SN1 mechanism. Okay. In SN1 mechanism, what happens is the leaving group come out, leaving behind a cation. And why the cation can come out easily, right? The cation can come out easily because just I will send you a message. You can send your message here so that I can see. Okay, I don't have to. I hope you can see the message. You must have received the message. Okay, yeah. On that account, you can send. Okay. So actually, this is SN1 mechanism. Okay, SN1 is what? Yeah, SN1 is a Br comes out easily, leaving behind a cation, and the ethanol is going to attack the cation, and the HBr comes out. And over a period of time, as the reaction progresses, the solution becomes acidic. Okay. And what about this one? Second option. So this also you took the same reaction conditions, but here the reaction has not turned into acidic. It remained neutral only. Why? Here it is not, the Br has not able to get out of the structure. Why? Remember what we discussed just now. If the Br is connected directly to the benzene ring, what happens is the Br lone pair participates with in resonance with the benzene ring, and because of this, the bromine and the carbon will acquire double bond character. And if it is a double bond character, it is very difficult for a normal reaction. This is just a normal nucleophile. You can see this is aqueous condition. No heat is given. Okay, no pressure is given. It is very difficult for us to react this. Okay, so the Br is going to stay connected to the benzene ring, and it is not going to come out. If it doesn't comes out, the reaction will remain neutral. Is it clear? So, and but what in this case, the Br is not connected to the benzene ring. It is connected out to, it is there is a one more carbon, and to that carbon the Br is connected. Is it clear? So it is not, it is actually known as benzylic carbon, which can form a very stable carbon. And what about this one? F minus is liberated. Here the Br was not able to come out, but here the F is connected to the benzene ring. It is able to react, but there the Br was not able to react. What's the reason? Yeah. So here also the F is participating in resonance. Is it clear? So, but still the F is able to separate out from the benzene ring, but in this case the Br was not able to come out. The reason is the NO2 group. NO2 group actually brings in positive charge at the ortho and para position, and this makes it very reactive. Okay, the fluorine can get substituted very easily. Okay, so we have seen that as you have more and more NO2 group connected with at ortho and para position with respect to the leaving group, the reaction becomes more and more easier to happen. Is it clear or not? Right? Now the next thing is, what about this one? Will this fluorine able to come out? Answer is no. They have written F minus is not liberated, but in this case they have told that F minus is liberated, but in this case they are saying that F minus is not liberated. So what could be the reason why F minus is not liberated? Yeah, you need to think. Though the NO2 group is there, but is it helping the F minus to come out? Is it participating in the resonance with the benzene ring? That you have to think. Is it participating the F minus? No, NO2 is not helping. Yeah, exactly. Because NO2 is not directly connected to the benzene ring. There is one more carbon, and next to that carbon, that NO2 is there. So it is not making, it is not helping the reaction to happen. It is not bringing in the positive charge. Is it clear? So that's why this F is not able to come out. But in this case, the ring became more reactive because of the NO2 group, so it reacted. Okay. So just a basic question, but very, very important. Now let's move to the new type of reaction and the last type of reaction in this chapter. Okay, those are elimination reactions. So first of all, what's the difference between the substitution reaction and an elimination reaction? Substitution means actually one group is displaced by another group. Okay, so here you can see the X is the group and it is displaced by Y. So you have Y in place of X minus. Is it clear? So it is a substitution reaction. And what's an elimination reaction? In elimination reaction, actually two groups are removed completely and no other group take their place. So what are those two groups which are removed completely? So one is X, another is H. Okay. So both are removed completely. Okay. So two groups are removed completely and no other group take their place. So what will happen to the bond? Two bonds through which the two groups are connected. Those bonds will connect among themselves and this will lead to the formation of a new double bond in the structure. Is it clear? This is called elimination reaction. Okay. Yeah, I will explain. Substitution is clear. What do you mean by substitution? Yeah, elimination means, I will write once here, one more time here, CH, H, CH2, Br. Elimination means two groups are removed completely and no other group take their place. Suppose if you remove H and Br, okay, so what will happen to these two bonds? What will happen to these two bonds? Will they continue to remain like this? Okay, Should I write? Because carbon is tetravalent. Okay, it always makes 4 bonds. So if I remove 2 groups, I remove the 2 groups from these 2 bonds. So how will I satisfy the valency of these 2 carbon atoms? Yeah, tell me. What will happen to these 2 bonds? Are they going to stay like this? Yeah. Yeah, they will going to no, but H we have already removed. H is removed, Br is removed. But from where the H is going to come? That is only when we are doing the hydrogenation reaction. When we are using the hydrogenation reaction. But now we are not using hydrogen. So what you need to do here is, in order to satisfy their 4 bonds tetravalency, you need to connect them among themselves only. Is it clear? Connect them with each other. So you have a double bond. So in elimination reaction, you have a double bond formation. Alkene, it is preparation of alkenes. Okay. Substitution, there is no double bond. One group goes out and another group come in and takes its place. It is a replacement reaction. On the other hand, if you have elimination reaction, 2 groups are completely removed. No other group come and join or take their place, and their bonds connect among themselves, leading to the formation of a double bond alkene. So this is elimination reaction. Okay, and elimination reaction require vigorous condition, heat. It always occur in the presence of heat. Remember this. So heat is represented by delta, base and heat. Lead to elimination. Okay. So let's see this elimination reaction. So I have taken this substrate. Okay. And I have taken a base. If I put them together, if I heat, what is going to happen? The base is going to come. This is CH2 Br. I will write it as CH2 and H. One H I put separately. The base is going to come. It is going to it will come and abstract the H plus. Okay. It will come and take away the H plus, and the electron will come like this and the Br will come out. Okay. Or what we can say here is, if you heat an alkyl halide with base, the H and Br, it is going to remove HBr. Base, if you heat, HBr is going to remove, because HBr is an acid. So HBr and the base will react and they will form a salt. Okay, and what will come in place of H and Br? What will come in place of H and Br? Who will come in place of H and Br? Yeah, double bond. Yeah, exactly. So there is a double bond. Okay, elimination reaction. Okay, and it happens in 2 ways, just like SN2 and SN1. In SN2, actually, if you take a strong nucleophile, similarly in elimination reaction, if you take a strong base, that strong base comes in and start abstracting the H, and the electron pair of the H start forming the double bond. Okay, and this carbon, because it is now started forming double bond on the left hand side, the Br actually will be removed. Okay, so Br is getting eliminated. H plus is taken away by the base. The electrons of the carbon hydrogen will come, and actually they will start forming a double bond, and because the middle carbon is forming a double bond, the Br minus will also come out. So all these things happening in just one step. It is, that's why it is known as single step, just like SN2. Okay, just like SN2, it is forming, it is happening in a single step mechanism. Is that clear or not? Okay. So, and because it is single step mechanism and the two molecules are involved, the rate is directly proportional to the concentration of the substrate and the concentration of the base. Is it clear? Because if you increase the concentration of both, they will react more vigorously. They will collide more frequently. Yeah, you can write it. Yeah. Okay. This is single step reaction. Transition state involves abstraction of H by the base and departure of leaving group, formation of a pi bond or a double bond. Yeah. This is how the reaction is happening. The elimination requires strong condition, vigorous condition. Okay. Heat, especially heat is required. So always one thing is, if you have heat, if you have strong base, then the elimination will happen. Okay. Yeah. So let's move to the next. I hope you have written or noted it down. Yeah, just note it down or take a screenshot so that you can. This is E2 elimination. Elimination by molecular, right? And it happens only in one step, in which the base, in substitution, what was happening? The substitution base was directly coming and attacking on the carbon atom on which the leaving group was there. Okay. But in this case, the base actually, in that case, it was known as nucleophile. Someone who attacks on carbon is known as nucleophile. But in this case, if you have taken heat and strong base, instead of attacking on carbon, it will come and join in itself on the H plus. It will take away the H plus. So removal of H plus by base will start elimination reaction. Not only H plus will be removed, the halogen atom which is adjacent to the carbon atom from which the H plus is removed, that will lead to the formation of a double bond. Okay. So I hope it is clear. Any doubts in this, you can just ask me. Okay. Right. So now this one. There is one more way in which the elimination can happen. Elimination can happen even if you have not taken a strong base, but you have taken strong heat. So if you have taken a tertiary and if you have not used a strong base, just you have used the heat, this can happen. And now actually what this is just like SN1. This is two-step elimination. Okay, SN2 actually was one step and this SN1 was two steps. Similarly, E2 was one step elimination and E1 is actually two-step elimination. So what happens here is you have taken water. Water is a polar solvent, right? That we know. And that will help. And if you heat it, that will help the carbon bromine bond to break away as carbon plus and Br minus. This is slow ionization of carbon Br bond that happens only in water if you are heating, leaving behind a carbocation. Okay. So this carbocation actually is stable because it is stabilized by resonance. It is stabilized by the three groups, not by resonance, but by the three alkyl groups which are close to it. Now this carbocation is not going to stay as it is because it is just an intermediate. So what happens here is the H plus is removed from the carbon atom adjacent to the carbocation so that the electron by which the H plus was connected to the carbon, those electrons can get between these two carbon atoms, the cation and the carbon from which the H is removed, and they can form a double bond. So you still have the same product, but this has occurred in two steps. So first step is departure of leaving group, leaving behind a cation. The second is removal of H plus. First step is removal of leaving group. Second step is removal of H plus. But in E2 reaction, both of them were occurring in just one step. Okay, just simultaneously. So you can SN1 also there is the same thing happen. So half of the path for the SN1 and E1 are same, right? Both proceed via carbocation intermediate. The leaving group comes out and leaves behind a carbocation. But if you are doing a substitution reaction, some nucleophile comes in and join to that carbocation, and the final answer is written. But if you have heat present, in the heating, the H plus is also removed from the carbon atom adjacent to a carbocation, and this leads to the formation of a double. Because this is slow step, this is RDS. So departure of leaving group is actually a slow step. It is a rate governing step. It is the difficult step which leads to the formation of carbocation after the removal of leaving group. And that happens by heating. Followed by removal of H plus, which lead to the formation of double bond. But by this step, the molecule is becoming neutral. It is regaining its neutral character. So it is not a fast. It is not a difficult step. It is an easy step, and it is a fast step. Okay. So abstraction of H by base, formation of a pi bond occurs in the fast step, and departure of leaving group, leaving behind a carbocation, is the slow step. Okay. Now suppose in this case we were not bothered. We were not bothered about the nature of the. We were not bothered about the nature of the alkene because we were having only one alkene formed. Okay, is it clear? There was only one type of alkene because all were the methyl groups. But in this case, suppose if you have an option to remove two hydrogen from two sides, then which alkene will you make? Which is going to be the main alkene, main product, and formed in major amount, and which is going to be the alkene which is formed in less amount. Okay, so that you need to decide. So let's discuss this. 2-bromobutane. The bromine is connected in the middle, and you have options to remove H from right hand side and left hand side. The two sides you can remove the H. Okay, clear? So if you remove H from the right hand side, the double bond will come in the middle. You will have 2 butene. Okay, and if you remove the H from the left hand side of Br, you will have a double bond at the outside region of the structure, that is 1 butene. So in elimination, you have main alkene which is formed in the elimination reaction is the more substituted or the more branched alkene. Okay, more branched alkene is the major product, right? More substituted, more branched. So how do we check? So let me write it here. This is the carbon, double bond carbon, double bond carbon, and what are branches? Branches are the alkyl groups which are connected to the double bond. So you have 2 alkyl groups connected to the double bond. So it is di substituted. There are 2 alkyl groups. Okay. And suppose if you form a alkene which is outside in the outer section, this one, this is having double bond and you are having one double bond and this is ethyl group, CH2 CH. So how many alkyl groups are there on this? How many alkyl groups are there? On one butene, only one alkyl group, this one. Only one alkyl group here. So this is mono-substituted alkene, singly substituted, and this one is di-substituted. And this is mono-substituted. So in elimination reaction, the major alkene which is formed in the elimination reaction is the one which is more branched or more substituted, or the alkene which has more number of double bond connected, directly connected to the doubly bonded carbon. Okay, so this is the major alkene which is formed in the reaction. And out of the two alkene, for every structure you need to think of the two alkenes or the three alkenes. So one will be the main alkene which is more branched. Okay, and that alkene is known as, out of those alkene, that is known as Setzef alkene. Okay, Setzef and Hoffen. Setzef alkene is a more branched alkene which has more alkyl group connected to the doubly bonded carbon atoms, and it is formed as a major product, main product for elimination reaction. Is it clear? Right? And which alkene is the minor product? Yeah. Yeah, Zaid. Minor product is the alkene which is less substituted. Okay, which is less branched. The alkene whose double bond is outside. Okay. And that is the minor alkene. So this is going to be the minor product. And this alkene is known as Hoffen alkene. The less branched alkene is known as Hoffen, and the more branched alkene, more substituted alkene is known as Setzef alkene. So out of for every structure you need to draw the Setzef and Hoffen. Okay, so it is the Setzef and this one is the Hoffen. Major product is the Setzef alkene. So for this alkene you can also try. So this is the middle carbon which is connected to Br, and you on three sides you have alkyl group. The two alkyl groups are same. Those are methyl groups. And you have one alkyl group which is the ethyl group. Methyl groups and ethyl group, right? So these two are same. So you can remove hydrogen from any one of them to make an alkene. No need to remove hydrogen from each one of them because both are same. You can consider any one of them to form the alkene. And this one. So you can have your different alkenes formed. You have taken a base. Okay. So if you have removed the hydrogen from the middle carbon, you will have this kind of alkene which is formed in the reaction. And if you have removed the hydrogen from the methyl groups which are at the top or the left hand side, you will have this kind of alkene. And if you count the number of alkyl groups, so this one is having 3 alkyl groups, 3 methyl groups. Okay. And this one is having 2 alkyl groups on the double bond. Directly, you need to look at the doubly bonded carbon, you need to look at how many carbon containing groups are directly joined to the doubly bonded carbon atom. And that will let you decide how much substituted that alkene is. So while doing elimination, the major product can be decided by thinking that by knowing the law that ZF alkene or the more substituted alkene or the more branched alkene or the more stable alkene is going to be the major product for the elimination. So this is going to be major product. Okay, because it is tri-substituted and this one is di-substituted, right? Similarly, 2-chloropentane also you can draw. You can remove the hydrogen either from the methyl group or you can remove hydrogen from the CH2 group. There are two groups on the either side of the carbon which is connected to Cl. So if you remove the hydrogen from the CH3 from the right hand side, right, and you will have pent 1E. And if you remove the hydrogen from this carbon left hand side, okay, you will have 2-pentene. Okay, so which one is going to be the major product? Pent-2-ene. Pent-2-ene is the di-substituted alkene. Is it clear? Yeah. It is known as, out of these two alkene, pent-2-ene is known as ZF and pent-1-ene is known as Hoffen. Right? Is it clear? Okay. So yeah, so let's do some more questions. I will give you a compound whose formula is C5. These are bromopentanes, H11Br, right? And it has 3 isomers. X, Y, and Z. This is X, Y, and Z are the 3 isomers of this. Right? X upon treatment with alcoholic KOH. Okay, always remember that with aqueous KOH you have substitution happening because aqueous KOH is mild. You have water. Is it clear? An alcoholic KOH and heat will make the condition more vigorous and that will lead to elimination reaction. In aqueous KOH, the condition with water, you have just substitution reaction, and with alcoholic KOH heat, you will have alkene form. Okay, so this is the compound. It has one isomer whose I'm calling it as X, and upon treatment with alcoholic KOH, it is giving only one alkene, C5H10, only one alkene. Okay, only one structural isomer is formed. So you need to tell me the structure of X. And there is another isomer which if you eliminate, right, which if you react it with alcoholic KOH and heat, it will not undergo elimination. No alkene is formed. Means it can't undergo elimination reaction. right? And there is another isomer of this C5H11Br, which upon elimination can give two alkenes, two different alkenes. So you need to tell me what is the structure of X, what is the structure of Y, and what is the structure of Z. They all have same formula C5H11Br, means they are the isomers. Isomers have same formula but different structure. An X isomer, if you react it with the alcoholic KOH and it undergoes HBr is removed, I will write it as minus HBr, means elimination is happening. And in this elimination, only one alkene is formed. Only one type of alkene. Either you remove H from this side or from that side of the R. Just now we have seen that we were having two types of alkenes being formed in the reactions. Okay. And two or more than two types of alkenes. And that was happening because we were having two different structures. Okay, that's why it was happening. But if you have a symmetrical structure, two different alkenes will not be formed. Only one alkene will form. So can you tell me the IUPAC name of X? What's going to be the IUPAC name of X? Yes, Ed. There are 5 carbon atoms. 5 carbon atom can be like this. It can be like this. Or it can be, I will give you the hint, you can select your answer. Cyclopentane. No, it is not a cyclopentane, it is an alkene. Though the cyclopentane is also the same formula C5H10. Yeah, but this is an alkene. Means we are considering only the open chain molecules, not the cyclic. Right? So I will give you the hint. These are pentyl bromides, okay, or bromopentanes. You can select which one is X, which one is Y, which one is Z. Okay, I have not written hydrogen, but just for simplicity, for in order to keep it easy. Yeah. So you can decide how many alkenes we are going to get from each one of them. Second one is X. Only one alkene is found. Yeah, X can be this one, correct. Good. Or X can have one more structure. one pentane, one bromopentane. That could also be the answer. Because if you have bromine at the end, you do not have any choice. You can remove only hydrogen from this side. That's it. Okay, X can have this structure or this structure. Okay. Yeah. And which structure could be Y out of these? This is first structure, this is second, this is third, this is fourth, and this is fifth. Yeah, it will not undergo elimination reaction. Why it will not undergo elimination reaction? What could be the reason? Yeah, your answer is correct. But what could be the reason why it can't eliminate, why it will not give any alkene? Yeah, Zed. Because it is alpha beta elimination reaction. Okay, 1-2 elimination reaction. So if the Br is getting removed from this carbon, the hydrogen should get removed from this carbon. Okay, and there is no hydrogen. There is no hydrogen here. No hydrogen here. No H available. The Br is there. Yeah, no, yeah, no beta hydrogen is there. Yeah, correct. Yeah. So because it is a alpha beta elimination, if from one carbon the Br is getting removed, from the other carbon the hydrogen should get removed, right? And there is no hydrogen means no elimination can happen. Okay. And which one of them could be this? What could be the structure of Z? So that it will give two alkenes. Yeah, the first one can give you two alkenes, correct? The hydrogen can remove from the left hand side or the right hand side, right? And this also, 2-bromobutane also will give you two alkenes, one pent 1 in and pent 2 in. Is it correct? Yeah. Okay. So now let's move to the next question. So what's going to be the answer to this problem? Zed, which topic is going on in your school? Yeah, correct, correct. Good. So why D? Yeah, why D? Take H from the right hand side from CH2. This is the right hand side. So, but if you remove the H from the right hand side, you will get this product A. Is A the answer or D the one which you told earlier? Which one? Yeah, why? D only. Why D? Yeah, correct. Why D? Because this will be stabilized by the resonance, right? Clear? There is a benzene ring and there is, suppose, so you need to bring the double bond just outside the benzene. Okay. And this will make the double bond very stable because this double bond will actually mix up with the benzene and it will get stabilized, right? Okay. So, yeah. And tell me this one. C. Yeah, why C? Yeah, Z. Correct. So why it is going to be C? Which one of the following compounds shall not produce propene? By reaction with HBr or followed by elimination with HBr? Yeah. What could be the reason? Yeah, your answer is correct. But why it is happening? Yeah, what could be the reason? Yeah, actually, you don't have to do the complete. Yeah, we will take HBr. Yeah, and propene has 3 carbon, which is just having 2 carbon atoms. That's it. Okay. So that could be the short trick of doing this question. No need to solve the complete question, right? So I hope this is clear, right? Okay. So just I was asking which topic is was going on in your school before the vacations, and which topic? Okay, F block. Okay, yeah. So now we will next topic we may start with alcohol and ether, right? Because that is very much interrelated to this topic which we are studying right now, and we can have the complete idea. Okay, so let's discuss one more thing, and that is substitution and elimination. So when you uh, how will you make out whether the substitution is going to happen or elimination is going to happen? That you need to choose. So when can you expect this thing to happen? This is substitution reaction, and this is elimination reaction. So how will you make out? And both happens with KOH. So how will you make out whether the substitution is happening or elimination is happening? Both are KOH. You need to look at some conditions. Now, what those conditions could be? Elimination actually requires a strong condition. It is endothermic in nature. Why? Because the weak bonds are forming, and the weak bond, because pi bonds are weak. Double bond, if you have a pi bond, that's are weak. So you require the heat needed to be supplied for the elimination reaction to happen. And you take alcohol as the solvent, C2H5OH. If you take alcoholic KOH, it is going to be elimination along with heat. That is very important. That's what I told earlier also, because eliminations are endothermic, so you need more heat to to compensate that heat which is being given to form a weaker bond. Okay, but if you have KOH aqueous, right, that is going to be the substitution reaction. This is mild condition without heat. If you take strong base and if you take alcohol, you are going to have elimination on the primary substrate, right? Suppose we can choose this one also, CH2Br. Yeah, what's going to be the answer to this problem? Whether it is going to be an elimination or a substitution reaction. And the second one is yeah. So first one is going to be the substitution. Why? This is primary, right? And this will be attacked and the Br will come out. And this is CH3, CH2, OCH3. Yeah. But what's going to happen for the next one? And why it is going to happen? This is a strong nucleophile. So it will go and attack on the carbon atom. So can the substitution happen on the carbon atom? Is the carbon atom accessible to the nucleophile? Tell me. No. Why? It is very much branched. Yeah. It is like this. It is tertiary. So it is not going to come and attack directly on the carbon atom having the Br group. So substitution can't happen by strong nucleophile. The strong nucleophile can't access the carbon atom because it is very much bulky, it is branched, it is directly hindered. So the next thing is, what can happen? Yeah, Zed. Yeah, it will not substitute. But the carbon atom is actually inside. Lot of branching is there. So the nucleophile cannot reach the carbon. But the nucleophile can easily remove the hydrogen, which is outside. So on tertiary substrate, you can't have substitution happen, SN2 happen easily. Because in tertiary substrate, the carbon is very much crowded. Yeah, so it will not substitute. Yeah, that is correct. So then what will happen? The elimination can happen easily. In elimination, because so this I'm cancelling out because the carbon is bulky, but the elimination can happen. In elimination, what will happen? The H will be abstracted and the electrons, and there is no problem in removing H because they are actually 9 hydrogens and they are outside. So yeah, yeah, yeah. But even you don't require any heat also. In tertiary substrate actually undergo elimination very easily. Okay, but they can't go substitution reaction. They can't go substitution reaction, and because the carbon is very much sterically hindered, it is crowded, it is a lot of branches are there. The carbon which is connected to Br is not reachable. So base, what a base will do? So it will go and extract the H plus. And what will happen to these electrons through which the H was connected? Yeah, they will come and get into the bond formation with this carbon and the Br will come out. So on tertiary substrates, you can have elimination very easily happen. Is it clear? Yeah. Zed, which is your school? What is your school name? Name of your school? Yeah. Okay, so I hope maybe 1st September they are opening, right? The vacations may be over or about to get over. Yeah. Okay. Yeah. So I hope this is clear. So substitution can happen very easily on less branch SN2, but for bulky group, you will have elimination. So look here. What has happened here? So you took ethyl bromide. Okay. O minus will come. And this is primary. This is 1 degree. It is having hydrogen. Yeah. So there is no problem in Br to come out. And this is substitution reaction. And this whole group has come and joined itself to the carbon atom, pushing out the Br. Right? So you have this main product substitution. But no elimination, very less. This is going to be the minor product. But if you take this alkoxide and brand alkyl bromide, tertiary butyl bromide, so this can't happen directly. Yeah. Why? Because this is very much bulky, very much branched. So nucleophile cannot access the carbon atom which is connected to Br. So what this nucleophile is going to do, this is going to extract H plus, and you will have H and Br getting removed, and you will have alkene which is. Okay, so you need to check. You need to check. Suppose if I need to prepare the CS3O, CS3, CS3 and CS3. So what should I take? This is substitution. Okay. So do I need to take CS3O minus? Here, this one, this set. Okay, what you did, you took O with CH3 and Br with the tertiary butyl. Is tertiary butyl methyl ether. Or what you can do is, you can use this also. You can take CH3Br and ether you can take as which one is more appropriate? The option A or the option B? Yeah, B option is more appropriate. It can happen more easily. Yeah, and this reaction, but in this case, this can't happen because it is branched. So this is elimination. You are not going to get an ether, and this reaction is known as Williamson ether synthesis. Right? You use an alkoxide, you use an alkyl bromide, but alkyl bromide should not be tertiary. Okay, then it can happen. Okay. So let me end today's class, and let's start alcohol with alcohol and ether in the next class. And that is going to be, many reactions are going to be very common, but there are going to be many new reactions also. Okay. So I hope you understood everything well, and do let me know if there is any doubt in the next class, right? Okay. So bye bye.